Lightning effects can completely transform the feel of your game, and in this tutorial, we're going to build a fully customizable, versatile, and robust procedural lighting system in Unity. So let's get right into it. The first step for procedurally creating a lightning bolt is to construct the shape of the lightning. And here's how we're going to do that. First, we're going to add 2 points, one for the origin and one for the impact point of the lightning. Let's connect them and name this connection as the OI segment. Then, we're going to add a new point in the middle of the OI segment. This will create 2 new segments, an OM segment that connects the origin with the middle point, and the MI segment that connects the middle point with the impact point. Finally, we can offset the middle point by some displacement value. Then, we're going to repeat this whole process for the existing segments by adding new points in the middle of each segment. This will split each existing segment into 2 new segments, thus resulting in a total of 4 new segments. As we did before, we're going to apply a displacement to the newly added middle points. It's important to note here that the allowed displacement should be around half of the original displacement for the point M. Each full iteration of this algorithm is called a generation. If we continue executing the algorithm for a couple of more generations, we're going to end up with a shape that resembles the one of a lightning bolt. However, lightning bolts often dispatch secondary, smaller bolts around them. They follow the same general shape while still having their unique look. Also, they're smaller and thinner. To mimic that behavior, we're going to allow each segment a chance to produce a new lightning bolt when splitting into 2 segments. This new lightning bolt will use the segments of the parent lightning bolt, but will continue to execute the next generation separately. This will result in a similar yet different looking lightning bolt. With that knowledge, let's see how we can implement this in Unity. Since the algorithm is based on adding points to define the shape of the lightning bolt, let's start by defining the lightning point class. For every point, we need to know its position, but we also need to know its orientation relative to the neighboring points, so that we can displace new points correctly. Finally, we're going to add one more property that defines the support for the next generations. If this property is set to false, all new neighboring points added after this point won't be displaced. This will add a bit of randomization to the look of the lightning bolt. Next, let's create a new class that will define a single branch of the lightning bolt. This class will of course contain a collection of lightning points. Additionally, it needs to hold variables that define the width and the emission intensity of the branch. By reducing the intensity of the new branches, we can make them appear smaller and weaker. Finally, let's add 2 helper variables that we're going to need for the execution of the algorithm. A creation generation variable that indicates in which generation of the algorithm has this branch been created, and a spawn point index variable that defines the index of the point that created this branch. We need this index so that we can continue executing the algorithm from this point after the branch creation. With supporting classes defined, we can now create the lightning shape generator class that will execute the whole algorithm. Since creating the shape of the lightning is its main purpose, let's start by defining the create lightning shape function. The starting point of the algorithm is the initial lightning branch that contains the origin and the impact point. Let's separate this initialization logic into a separate function. First, let's transfer the positions to the local space of the lightning. Then, we need to calculate the local axis of the points so that we can displace new points correctly. We can calculate the forward axis easily and then use it to construct the right and the up axis. We're actually going to use this in a couple of places, so let's extract this logic into a separate function. Finally, store the origin and the impact points into a new collection of points and assign them to the initial lightning branch. Also, the initial lightning branch needs to be the widest and the brightest, so make sure to set the variables to a maximum percentage of 1. Return the branch at the end of the function. With the initial branch created, we can start with the execution of the algorithm. Make sure to calculate the number of branches in every iteration, since new branches will be added during the execution of the algorithm. As we've said earlier, the shape construction is executed over multiple generations, so let's add a for loop that goes over them, starting from the initial generation. Also, let's define the maximum number of generations for the algorithm. Note that each new generation multiplies the total number of points by 2, so make sure to use a reasonable number of generations. Then, inside each generation, we need to go over all the lightning points and add new points in between the existing points. Start by referencing the current and the next point. Then, find the middle position in between them and create a new point on that position. Finally, insert it into the collection of points for this lightning branch. Also, make sure to offset the point index to skip the newly added point for the next iteration. We've now implemented the addition of points in every generation, but they're currently added exactly in the middle, forming a straight line. The next step is to add a bit of displacement to every point so that they would form a much more interesting shape. Let's start by adding a maximum allowed displacement as a serialized variable. Then, let's add a couple of variables that will ensure we get a deterministic result every time, based on the randomization seed that we specify. Also, make sure to initialize the randomization generator at the start of the function. Then, let's go back to the generate lightning shape function and add a bit of displacement to the position of the middle point. First, cache the local orientation axis of the current point since we're going to need them. Then, let's calculate random offset values for each axis and use them to offset the position of the middle point. Since the position of the middle point changed, we need to correct the orientation axis of the current and the middle point. And that's it. We've now successfully added the displacement to the points. Let's see those gorgeous results. Ugh, this looks nothing like the lightning. The main issue here is that we haven't reduced the maximum allowed displacement for every new generation. So let's fix that. Hopefully, this should be very easy to do. Let's add a new variable that controls how much should the displacement be reduced in every generation. Then, in the generate lightning shape function, limit the maximum possible offset for the current generation and update the logic for offset calculation of the middle point. And that's it. Let's check out the results. And here are the results. Finally, a nicely detailed shape of a lightning bolt. I feel we've reached a solid look for one lightning, so let's implement the support for multiple lightning branches. To support that, we're going to add a couple of variables. This variable specifies a base chance for spawning a new branch at a certain iteration. However, this chance needs to increase with every new generation, so let's define this increase multiplier for that. Next, we need to limit the maximum number of branches we're going to allow and specify the reduced emission intensity and the mesh width for every new branch so that they would appear smaller and weaker. With these variables defined, let's go back to the generate lightning shape method and specify the chance of creating a new branch in this generation. Then, after adding a new point, let's check if a new branch should be created or not. In case it should, add a new lightning branch to the collection of branches. We just need to duplicate all the points of the current branch to the new one. Since the algorithm will continue for the current branch, we need to cache the creation generation and the index of the point that spawned this branch, so that it can continue with the execution of the algorithm later on. Also, we need to reduce its emission intensity and width. Finally, we need to tweak our current algorithm a bit to correctly resume the iterations on the new branches at the beginning of the generate lightning shape method. Also, since the newly created branches need to continue the algorithm execution from the point that spawned them, we need to adjust the inner loop to start from the correct point index. That's it. Let's check out the results. Everything seems like it's working correctly. The new branches are being spawned and the lightning shapes looks interesting and convincing. Once we've created the shape of the lightning by defining the points, we need to construct a mesh around them. To do that, we're going to define a set of vertices around each point. Then, we're going to distribute them in a circle. If you use more vertices, you will get a smoother circle, but it'll be more expensive for rendering. So let's use something like 16 for now. Next, we're going to connect these vertices with the corresponding vertices of the previous and the next point. Also, if we add an additional connection to the neighboring vertex of the one we've just connected to, these connections will form triangles, which are essential blocks of every mesh. We can now provide this data to the GPU so that it would render a solid mesh for us. Wow, this already looks so much better. The final part of this step is to give a proper color to our lightning. I'm going to use an unlit shader with a base blue color. And of course, let's add some blue emission color and crank up the intensity. There we go. That's looking much more like an electrical discharge caused by imbalances between two differently charged objects. Perfect. If you feel like this visual explanation was enlightening to you, please leave a like, it will help us a lot. Now let's see how to create this effect in Unity. Create a new script called Lightning Mesh that will be in charge of creating a new mesh asset. Let's start by creating some internal variables and a default constructor for the class. Next, construct the createLightning method that creates a mesh asset for the provided lightning branches while keeping track of the segment resolution and size. The first thing we're going to do is check if we need to recreate the mesh or if the one we've already created will work fine for the provided branches. The current mesh can be reused if it has the same amount of points and the same amount of vertices per point. In case we need to construct a new mesh, we're first going to dispose of the old one and then create a new one with the provided settings. Let's separate the creation process into a new method. The first thing we need to know is how many vertices and triangles this mesh requires. After calculating the required number of vertices and triangles, we can allocate the required memory. We're going to fill in the mesh data required for every lightning branch and finally assign the data to the mesh asset. However, this method is getting a bit too big already, so let's extract the mesh data creation logic into a separate method. This method will fill in the initial data for a specific lightning branch while skipping over the data filled by other branches. We're going to place all the vertices to 0 and assign the same UV coordinate to every vertex. However, note that this UV coordinate holds the intensity of the lightning emission and not the texture coordinate it usually contains. It's a common practice to store the custom data in UV channels that aren't being used. This way, we won't break the batching when rendering different lightnings that use the same material, even though they have different emission intensities. Next, we need to add triangles that connect two segments of vertices. Since we're connecting the vertices of the current segment with the previous one, this logic needs to be skipped for the first segment. Again, this function is getting a bit large, so let's separate this logic into another function. Finally, update the offset variables for the next lightning branch so that it doesn't override the data we've just entered for this one. And this is the method for adding triangle indices between two sets of vertices. First, it calculates the first and the last vertex index of each segment. Then, it goes over every vertex in the segment and connects it with the corresponding vertex of the next segment and its neighbor to form the first triangle. The second triangle consists of two neighboring vertices on this segment and one on the next segment. One last thing we need to do is to prevent overflow while iterating over the vertices so that the last vertex correctly connects to the first vertex in the segment. We have now successfully implemented logic for creating the mesh asset, so we can go back to the createLightning mesh method where this whole journey started. To continue where we left off, at this point of the method we have a mesh that can represent the lightning shape. We just need to update the position of its vertices to mimic the shape of the lightning and then assign these updated vertices back to the mesh. As you probably already noticed the pattern, we're going to separate this logic into a new function. All that this function does is position vertices in a circle around the lightning point while keeping the orientation towards the next point. The final thing left is to implement a cleanup method for disposing of the created mesh. We can now create a lightning shape and construct a mesh asset for it. Let's create a class that will connect these two parts and control their execution. Name it Procedural Lightning. This class is pretty simple. It references transforms of the origin and the impact point, as well as the lightning shape generator. Additionally, it provides controls for the number of vertices around each point and the width of the lightning. Also, it contains references to the mesh filter component that will hold the lightning mesh we create, and the lightning mesh component that will create it. And here's the logic that will guide the update of the lightning. First, We request the new lightning shape from the lightning shape generator component and then provide that shape to the lightning mesh class that will create a mesh asset from it. Finally, we just need to assign this mesh asset to the mesh filter component so that it can be submitted for rendering. Back in the editor, we're going to create a new empty object, name it Procedural Lightning, and then assign the Procedural Lightning component to it. After connecting the references to the origin and the impact point transforms, add a new lightning shape generator component and assign its reference. The lightning mesh is being created now, we just need to render it, so add a new mesh renderer component. And here's the lightning mesh we've been expecting. However, it's currently pink since we haven't assigned any material to the renderer. Let's create a new unlit shader for the lightning that will support the reading of emission intensity that we packed into the UV channel of the mesh. Open it up and set it to a transparent unlit surface type. Then, declare two new color properties, one for the base color of the lightning and one for the emission color. Just make sure to set the emission color to an HDR color mode. The shader is very simple. The only difference from a basic unlit shader is that it scales the emission intensity based on the UV coordinate, since we packed the emission intensity multiplier into it. With the shader complete, create a new material from it and set up the colors. The base color should be dark blue, while the emission color should be a bit brighter and have an emission intensity of something like 12. After assigning the material to the renderer component, we can finally stare at our beautiful creation. Even in this static form, I think it looks pretty good, don't you think? But let's add some motion to it. The third step for creating procedural lightning is all about adding movement to our mesh to get that realistic electric feel. And we have three different ways to bring this effect to life. First, we can regenerate the entire lightning shape by rerunning the shape creation algorithm. This will create a brand new shape each time, which results in a bigger, more dramatic shift. Since it results in a larger movement of the effect, it should be used sparsely. Next, we can change the visibility of the branches every few frames. This gives the effect of sudden bursts of energy, adding a lot of dynamic tension to the lightning without changing its overall form. Finally, we can horizontally move the points that we generated in the first step towards the origin point. The trick here is to move each point based on when it was generated. The points from earlier generations move more, while the later ones move just a little. This makes the movement feel natural and layered. With these three approaches combined, we can make the lightning feel much more alive and dynamic. Let's see how to implement all of this in Unity. In the lightning shape generator class, let's add variables for the minimum and maximum delay between the shape updates. Also, define helper variables for the past time from the last update and the delay after which we need to update the shape. Next, replace the initialization of the randomization generator with the check for shape update function that we're going to create. And here's the function code. It starts by updating the time passed from the last shape update and checks if enough time has passed in order to update the shape. If it has, the randomization seed is increased, which will ensure that a new lightning shape is produced. Then, we need to reset the time from the last shape update and calculate a new random delay for the next update. No matter if the shape has been updated in this frame or not, the randomization generator is initialized for the current randomization seed, so that we get the deterministic result. Let's see how this looks now. After only a small tweak, we got a very dynamic result. The lightning changes shapes at irregular intervals, which mimics the unpredictability of the lightning. But it's still looking a bit stiff. Let's change that by controlling the visibility of branches. Again, we're going to start by defining some new variables. A branch invisible chance variable that specifies a chance that a certain branch will be invisible, and a multiplier that increases this chance for every new generation. Also, define the maximum chance that a single branch can be marked as invisible and the minimum and the maximum delay for updating the visibility of the branches. As with the shape update, we need to define some helper variables that are required for implementing this functionality. The first two variables have the same responsibility as the ones for the shape update, while the visible branches indices variable represents which branches should be visible by caching their index. Now, go to the bottom of the create a lightning shape method, just before the return statement, and insert the call for the update branches visibility function we're going to define. But before we define it, make sure to reset the visibility update timer whenever the lightning shape changes, so that we ensure that the visibility updates on the exact same frame. And here's the code for the update branches visibility function. It's very similar to the shape update function. First, it updates the elapsed time from the last visibility update, and if enough time has passed, it randomly updates the list of visible branch indices. Then, it makes sure that the branches that are invisible are removed from the collection of lightning branches. And that's it. Let's see the current state of the lightning. Personally, this seems like the most important step when creating procedural lightning. It just makes the effect so much more dynamic and alive. But we can increase it even more by adding horizontal movement. Let's start by defining the minimum and maximum allowed horizontal offset for a specific point. Then, we're going to add two helper variables. A midpoint max horizontal offset variable that specifies the maximum horizontal offset for this shape update, and another variable that will dynamically increase the allowed horizontal offset over time. We're going to update them whenever the global shape of the lightning changes, so let's hop into the check for shape update method. There, whenever the global shape changes, randomly calculate a new maximum horizontal offset. Finally, update the current offset of middle points based on the time passed from the last global shape update. The last thing left to do is to update the logic for positioning the middle point inside the generate lightning shape function. Currently, we're placing the new point exactly in the middle between two neighboring points. Change that so that the point is offset more toward the origin point based on the current middle point percentage. Also, reduce that percentage based on the current generation of the algorithm so that the points that represented the smaller details of the lightning are moved less than others. And this is the final look of the lightning. It's dynamic, unpredictable, and powerful. I really like it. However, it can be a little taxing on the CPU, so in one of the next videos, we're going to take a look at how we can transfer some of the logic to the GPU by using the compute shaders. So if you're interested in learning how to do that, make sure to subscribe so you won't miss it. If you're shocked that this video is over already and you want to continue learning with our educational animations, take a look at this video. It visually explains every step of a triplanar mapping technique. And that's it. Thank you for your time and good luck with your creations.